Hello and welcome to lesson number 20, straight lines in the coordinate plane. This is the first lesson in grade 13. We've now finished grade 12, so welcome. In order to first talk about straight lines in the coordinate plane and so on, what we first need to define is what a straight line is. In his book, The Elements, Euclid describes a straight line as being a line which is even with all the points which are within it. Now this definition is to imply that the line is symmetrical, the line is continuously having the same direction and all of that, but for our purposes we'll be defining a straight line as a collection of points that together form a path, and along that path there is no change of direction. We will be using this definition when we're thinking about straight lines. So first off, how do we define a straight line in the Cartesian coordinate plane? If you don't know what a Cartesian coordinate plane is, click this video on the top right here. Moving on. A line like this can be defined if we know 2 points, well, at least 2 points on the line. It can be defined as such. Let's suppose that we know this point here, which I'm going to label as x1, y1. So this point is the points with the coordinates x1, y1. Let's say we know another point over here, and let's suppose that this point here is x2, y2. And we know that both of these points lie along this line. Since we know that this line is having a constant direction, we could do something like this. Let's suppose we draw a horizontal line that cuts across this point and a horizontal line that cuts across this point like this. If we draw two lines like this, since the line that we are considering has a constant direction, we know that this angle should be equal to this angle. Let's now suppose that we want to find the coordinates of another third point. Let's say this point over here, and let's call this point a generic x, y. For this point as well, if we draw that same horizontal parallel to the other two horizontals as such, then we know that the angle made by this horizontal to this line is also going to be equal to that same angle, theta. So we'll mark that down as this angle is also going to be equal to theta. Given this, we can draw the following triangle. We can draw a vertical down from this further point on the right side here, down like this. If we draw a vertical like that and it intersects the horizontal at this point here, we know that this angle is 90 degrees. Similarly, we can draw another vertical downward from this point here, the point of interest, and we also know that this angle here is also 90 degrees. Now we're pretty much done with the construction we need to figure out what this point x, y is. Consider this point here to be the point D, let's say, and let's suppose that this point here is A, this point here is B, and the point we're interested in is this point, which we're going to call we'll call this point P. Let's suppose that this intersection here is C. From Cartesian coordinates, we know that AD is a horizontal, therefore its length is going to be the difference of the two x coordinates. So therefore AD here is going to be x2 minus x1. So AD is equal to x2 minus x1. In a similar way, considering BD is a vertical, therefore BD's difference of coordinates is going to be equal to its length. Here the difference of the coordinates is only the y coordinates, it's y2 minus y1, since D also has the same y coordinate as A, as in y1. So therefore BD length is y2 minus y1. Now if we consider the triangle ABD, we can see that within the triangle, tangent of theta is BD divided by AD. So tangent of theta is BD divided by AD. This set of equations is gotten from the triangle ABD. So we'll mark that this set of equations is gotten from the triangle ABD. Let's now consider the triangle APC and consider similar relationships in this triangle APC. Considering APC, we have PC length and AC length. PC is vertical, AC is horizontal. Since AC is horizontal, the AC length is going to be the difference of the x coordinates. So therefore AC equals, and the difference of the x coordinates here is x and x1. So therefore the difference of x coordinates is going to be x minus x1. So x minus x1. And then the y coordinate difference, which is going to be PC here, this vertical difference is going to be this y coordinate y minus this c's y coordinate, which is going to also be equal to y1. So therefore PC is equal to y minus y1. Now considering tan of theta within the triangle ACP, we can see that tan of theta is PC divided by AC. So within this triangle, tan theta is PC divided by AC. These three were found from triangle APC. Now then, considering this, the tangent of theta has one value when we consider triangle ABD and another value considering triangle APC. Combining these two, we can see that BD, actually we'll write on this side PC divided by AC is equal to BD divided by AD. Since the two values of tan theta are both the same exact value, so they must be equal. Therefore, the two right hand sides must also be equal. So we have this. Substituting in our values, we can see that y minus y1 divided by x minus x1 is equal to, and then BD here is y2 minus y1 and AD is x2 minus x1. So it's equal to y2 minus y1 divided by x2 minus x1. This is the most basic way to define a straight line. A straight line is a line where given 2 points, let's say x1, y1 and x2, y2, we can have any other point along that line satisfying this equation. Now here there are some conditions, of course. x2 and x1 should not be equal to each other, because if x2 is equal to x1, then we have the issue that we are considering only the one single point. So we should not have that. x1 should not be equal to x2, as in we should not be considering the same exact point. Furthermore, this thing has a little bit of issue when y is equal to y1. We can see when y is equal to y1 and x equals to x1, i.e. the coordinate of x comma y is the same as the coordinate of x1 comma y1, we get an issue where we have 0 divided by 0. Over here, this point should not be this point or this point because of this divide by 0 issue. To combat this issue, let's multiply both sides by x minus x1. When we do that, we can see that we get y minus y1 equal to, I'm going to put this whole thing here inside of a single block and say y2 minus y1 divided by x2 minus x1, and the other part is going to be x minus x1. This now is a little bit of a better format for our straight line. It says that y minus y1 should be equal to this value here, which is a constant because this y2 and y1 and x2 and x1 are predetermined. We already know those coordinates, they are definite values, and multiplied by x minus x1. Now to be clear, it doesn't have to be x1 here, it could be the other point also. You don't have to choose the lower x coordinate and lower y coordinate point. It doesn't matter like that. You can choose anyone you want. So then, moving on. This is not the usual format, or not one of the usual formats that we write a line. We instead simplify this further to say that y minus y1 is equal to y2 minus y1 divided by x2 minus x1, and here we take this x, we multiply this thing by x, take this negative, this thing, multiply it and separate the two. So we write it as that thing times x minus the same thing y2 minus y1 divided by x2 minus x1 times x1. And then what we do is we take this y1 to the other side and we say that y is equal to y2 minus y1 divided by x2 minus x1 times x, and this whole thing, this negative, this part and this y1 which is going to come to the other side, I'm going to take into one bracket and say plus y1 minus y2 minus y1 divided by x2 minus x1 times x1. And here we do a thing, we consider this thing here, this value here inside of this bracket and this value here inside of this bracket. Here we can see, since y2, y1, x2 and x1 are all constants, this is just some kind of constant. Same with this thing, here y1 minus this whole thing times x1 is itself also a constant. We name this constant here as m. So we say y equals m times x. So here we have m times x plus, and then we name this second constant here c. We have y equals mx plus c. This is one of the standard formats for a straight line. It's probably the first one you learned, maybe not, but it is very likely the first one you learned. This is what we call the gradient intercept format. Here, m is what we call the gradient. The gradient is basically how much y changes when you change x by a certain amount. This could be interpreted as changing x from x1 to x2 and observing what happens to y as it changes from y1 to y2, taking that change of y and dividing by the change of x, effectively finding the change of y per change of x. And then this c also has its own value. C is what we call the y-intercept. The reason for this is that when x is equal to 0, i.e. we are on the y-axis, the value of y corresponding to that is going to be equal to c, because when x is equal to 0, this term is equal to 0, meaning that y equal to c. So what this means in our diagram here is, given this format, at the point where we reach the y-axis, as in this point right here, the correspondent y value is going to be equal to c. This is a useful format because it gives us some interesting behaviors which we will discuss, but it is not the best format for most general cases. We will now discuss some special properties of this case and then move on to some other ways that we could express straight lines. But this is one of the most common ways to express a straight line. It is known as the gradient intercept format. One of the most useful properties of this format is that m is equal to tan theta. Here we can see up here, tan theta from this equation is going to be BD divided by AD, which is y2 minus y1 divided by x2 minus x1. So therefore, m is tan theta, where theta is the angle between the positive x direction and where the line is. So if we draw this out on a graph, we can see, given a graph like this where we have the standard x-axis, of course, we have the standard x-axis, the standard y-axis, and a straight line going like, let's say, this. Then the angle that this line makes with the x-axis is going to be theta, and if you take tan of theta, it is going to give you the gradient of this line. This becomes useful when we want to find the angle between two straight lines. So to do that, let's consider example. Let's consider two straight lines, let's say one like what we've drawn here, and another one like this. Here we can see the second straight line has a greater angle than the first straight line. Marking this out, let's suppose that the greater angle straight line has an angle of alpha and the lower angle straight line has an angle of beta. So let's call this angle here alpha, and let's suppose this angle here is beta. Here we can see these two lines intersect at a point. If we consider this point and draw a horizontal at this point, then we can see some interesting things. For the first line, since the horizontal is parallel to the x-axis as in the direction of the x-axis is the same as the direction of the horizontal, we can see that this angle here is also beta. Furthermore, we can see that this angle here is alpha. Now then, the angle we are really interested in here is the angle between this line and this line. Let's suppose that the line with angle alpha is going to be given by y equals m1x plus c1, and let's suppose the other line is going to be given by y equals m2x plus c2, where m1 and m2 are the gradients of the two lines and c1 and c2 are the corresponding y-intercepts. Given this, we know that the tangent of alpha is equal to m1, and we know that the tangent of beta is equal to m2 from the theory that we established just a few moments ago. So we have this. Let's put a box around this, taking these as values. We will be using them later. Let's now consider the angle between these two lines. The angle between these two lines is this angle here. Here, since alpha appears to be the bigger angle, theta is going to be alpha minus beta. However, we cannot guarantee this. We could be taking it the other way and we could have alpha being smaller than beta, in which case it would have to be beta minus alpha. To avoid confusion like this, we'll just suppose that the angle theta is the absolute value of alpha minus beta. As in, there's one line with an angle alpha, there's another line with an angle beta, and the angle between the two lines is the absolute value of alpha minus beta. So we just remove one of the angles from the other angle. Now then, how do we find the value of this line here? This angle here. Well, what we're going to do for that is to take this expression and take the tangent of both sides. So we're going to take the tangent of theta, and that's going to be equal to the tangent of the absolute value of alpha minus beta. Now here we have the absolute value of an angle alpha minus beta. Recall from this lesson here in the top right that if you have tan of negative alpha, or let's say negative theta, the tangent of a negative angle is negative the tangent of that angle. Considering that, let's say tan negative x is equal to the negative tangent of x, and the tangent of x is of course equal to the tangent of x. So if we consider here the tangent of the absolute value of x, when x is positive it is the value itself, and when x is negative it is negative that value. Therefore the tangent of the absolute value of x is also equal to the absolute value of the tangent of x. This is coming from the fact that the sign being on the inside and the sign being on the outside are the same thing. We can see the tangent of positive alpha is the positive tangent of alpha, and the tangent of negative alpha is the negative tangent of alpha. So therefore we have this property. Using this property, let's write the tangent of the absolute value of alpha minus beta as the absolute value of the tangent of alpha minus beta. So therefore we have the absolute value of the tangent of alpha angle minus beta angle. Now then, recall this lesson here where we found that the tangent of alpha minus beta for some angles alpha and beta is tan alpha minus tan beta divided by 1 plus tan alpha tan beta. From this identity, we are going to go to the next page here. From this identity we can see that tangent of theta is equal to the absolute value of, and on the inside tangent of alpha minus beta is going to be equal to the tangent of alpha minus the tangent of beta divided by 1 plus the tangent of alpha times the tangent of beta. Now then, we know what tan alpha and tan beta are from up here. What we're going to do now is substitute those into this expression that we have. Tan alpha is m1 and tan beta is m2. Therefore what we have is that the tangent of theta is equal to the absolute value of tan alpha is m1, so we have m1, minus tan beta is m2, so we have m2, divided by 1 plus tan alpha is m1, tan beta is m2. So this is the result that we want to get, and we want to take this result, we want to take its absolute value because we don't care about negative angles, the negative angle and positive angle. What we want is the absolute size of the angle. So we take the absolute value, and that is going to be equal to the tangent of theta. Now then, since the tangent of theta is a one-to-one function, we can take this to the outside and we can say, applying the inverse function, theta is going to be equal to the tangent inverse of this thing here, which is going to be the absolute value. So we can write like this, the tangent inverse of the absolute value of m1 minus m2 divided by 1 plus m1 m2. Here we can see clearly the advantage of using the intercept and gradient formula. With the gradient intercept formula, if we know the gradients of two lines, we can find the angle between the two lines. Now note here, the angle we are going to get by using this method is going to be the acute angle between the two lines. This is because the tan inverse is only defined in between the angle outputs of negative pi by 2 and pi by 2. So here, this is only going to output some angle between 0 and pi by 2 since we are taking the absolute value. If you want the acute angle, you need to take 180 degrees and subtract this angle from that, or in radians, pi radians, and subtract the tan inverse of m1 minus m2 divided by 1 plus m1 m2's absolute value. The other major useful feature of the gradient intercept format is actually a result of this. From here we can see that if we have two lines, the angle between them's tangent is going to be equal to the absolute value of m1 minus m2 divided by 1 plus m1 m2. Here if we take this and we do 1 divided by it, we get that 1 divided by the tangent of theta or the cotangent of theta. So cotangent of theta is cot theta is going to be equal to, and then taking this thing we have 1 plus m1 m2 divided by m1 minus m2. So if we take 1 divided by, we have 1 plus m1 m2 divided by m1 minus m2. So then what we are going to be thinking about is what happens when the two lines are perpendicular to each other, i.e. if we draw out these two lines with their gradient intercept formats, this line is going to be like this line is going to be like this, where the two are perpendicular to each other. So here we can see they're perpendicular, there's 90 degrees in between them. This line, let's say, is going to be equal to y equals m1x plus c1, and this line here is going to be equal to m2x, y equals m2x plus c2. Given this condition, we can see the angle between the two is equal to 90 degrees. If we take the cotangent of 90 degrees, we know that's equal to 0. So therefore, on the left hand side, what we have is 0. So we have 0 equals, and on the right hand side, what we have is the absolute value of 1 plus m1 m2 divided by m1 minus m2. So we can split that thing and we can write that the absolute value, this is the absolute value of 1 plus m1 m2 divided by the absolute value of m1 minus m2. From observation here, we can see that m1 is not equal to m2, since these two are definitely not in the same direction. Therefore this thing is non-zero. This m1 minus m2 bit is non-zero. So we can multiply it to the right side and get that absolute value of 1 plus m1 m2 must be equal to 0. Since the absolute value of 1 plus m1 m2 is equal to 0, 1 plus m1 m2 must equal to 0. So 1 plus m1 m2 must equal to 0. Meaning that m1 m2 is equal to negative 1. This is another property that we can derive, as it's derived from the first property of the angle between two lines using the gradient intercept format. But it's a little special case which we very often use as a little shorthand. If two lines are perpendicular to each other, we can see that the gradient of the first line times the gradient of the second line must be equal to negative 1. We can use this wherever we want. It's taken as being a standard normal thing. We can use it without having to explain it. If we have two lines in gradient intercept format, the gradient of the first line times the gradient of the second line being equal to negative 1 indicates that the two lines are perpendicular to each other. So that's all about the good things of this line. Let's now consider some disadvantages of the format y equals mx plus c. One of the main disadvantages is that we cannot represent vertical lines. Why not? Well, consider the formula that we needed to get m. m is y2 minus y1 divided by x2 minus x1. If we draw a vertical line, let's go down here and let's draw a simple vertical line. This vertical line means that its x-coordinate here and here are all the same. Anywhere along this line, its x-coordinates are the same because the line is vertical. It has no horizontal left or right movement. So therefore, let's say that this coordinate here is x0, y1 and this coordinate here is x0, y2. Here the two x-coordinates are the same but the y-coordinates are different. If we consider the gradient m is going to be the difference of y-coordinates. So y2 minus y1 divided by the difference of x-coordinates, which is x0 minus x0, which is going to be y2 minus y1 divided by 0. We have a divide by 0 here. This is not allowed. It should not happen. What is actually happening here is that as we make this line steeper and steeper, its gradient is actually going to approach infinity. It's going to approach one of the infinities. If we go from a positive gradient, it's going to approach positive infinity. If we go with a line with a negative gradient, it's going to approach negative infinity. But what's happening here is that as we approach a vertical line, our gradient is going to go to infinity. Due to this and due to the fact that we cannot represent an infinity very nicely within our equation, because for y equals mx plus c, we cannot just put an infinity into here. It's not how it works. That, however, is not going to be a problem with this next formula for a straight line that we're going to be discussing now. The next format looks like this. Given a line, let's suppose that the perpendicular distance of that line to the origin is p. And let's also suppose that the angle that perpendicular makes the x-axis is alpha. Given this, then this line here is going to be given by x cosine alpha plus y sine of alpha equal to p. This holds true for all alpha and p. So here we have another way to define a line. In order to prove this thing, what we can do is simply consider some point on this line. Let's say this point over here. This point, let's suppose, is given by x comma y. Then here we can see, if this point is given by x comma y, dropping this vertical down like this length here is the value x, so here to here is the value x, and this length here is the value y. So here this is x and this length is y. Now then let's drop this perpendicular from this point down to the line P of length P. Here we can see that this angle inside is alpha, and x times the cosine of alpha is this partial length here. This partial length is x times the cosine of alpha. Here we can also see this angle here is 90 degrees minus alpha. So therefore this angle here is going to be alpha, since this total angle is 90 degrees. Now then, considering that, we can see within this triangle which I'm going to draw here, within this triangle we can see that the length which I'm going to mark here is equal to y times the sine of alpha. So this part of the length is equal to x times the cosine of alpha, and this length here is equal to y times the sine of alpha. So therefore the total length p can be seen to be equal to x times the cosine of alpha and y times the sine of alpha. Now here this is a limited example where alpha is between 0 and 90 degrees and p is going to this direction and so on. However, this format works for all angles alpha and for all perpendicular distances p. The advantage of this is that given this format, we can represent vertical lines, horizontal lines, lines going through the origin, and any other form of line you can think of. You can just plug in the corresponding alpha and the corresponding p. Of course, there's a small caveat here. When our line gets really close to the origin, like something like this, there is no length of perpendicular. So we cannot really draw the perpendicular line's length, which means that we cannot find the angle alpha of the x-axis relative to the perpendicular. Instead, what we do is find this angle here, which is going to be pi by 2 minus alpha in that case. Well, here really what we want is the angle alpha, but we can find this angle pi by 2 minus alpha for any single line, and then use that, we can use that to find the angle alpha which we need to substitute into this formula. So yes, if you draw the line through the origin, it does look like there's no line of the perpendicular for us to draw the angle alpha to. However, this can be combated by redefining what alpha is. So here, all we have to do is find the angle that the perpendicular makes with the x-axis. Here, of course, if you have something like this, we need to consider this angle here from the x-axis in the clockwise direction, that angle, and then take the cosine of that, take the sine of that, plug it into this formula, and it will give you the equation correspondent to that line. You can then use this equation however you want. You can rearrange it to different formats and such in order to find different properties of the lines you found. So we're not going to be elaborating any further on this form of a straight line. We might get back to it later, but for now, let's go to the next form of a straight line that we can have. Here, for this line, what we're going to do is have to know the x-intercept and y-intercept of this line. Here we can see I've marked them out. The x-intercept is the point where we cross the x-axis, i.e. some value of x and y equals 0. And the y-intercept is the point where we cross the y-axis, i.e. x equals 0 and some value of y. The x-intercept in this case I've marked as x0, and the y-intercept I've marked as y0. Now then, considering a generic point x, y on this line, if we consider the generic point x, y, we can see that the gradient of this line will be 0 minus y0 divided by x0 minus 0. It has to be equal to, let's say, this coordinates minus this coordinates, which is going to be y minus y0 divided by x minus 0. We must have this thing here being equal. If we take this thing and we rearrange it, we can see, taking this x to this side, we can see negative x times y0 is equal to x0 times this thing here, which is going to be x0 times y, and then minus x0 y0. Cleaning this up a little bit, taking this x0 y0 to this side, taking this x, y0 to this side, we can see x0, y0 is equal to x0, y plus y0, x. What I'm going to do now is divide both sides by x0, y0. Doing so, what we get is that x divided by, in this case here we can see when we divide by x0, y0, the y0 is going to be cut and we're going to have divide by x0. So x divided by x0 plus, for this term, when we divide by x0, y0, the x0 is going to be cut and we have a divide by y0. So we have y divided by y0 equal to, here when we divide this side by x0, y0, we get x0, y0 divided by x0, y0, which is equal to 1. So therefore we get the format of x divided by x0 plus y divided by y0 equal to 1. What this means is that given a line with x-intercept x0 and y-intercept y0, then that line will be given by x divided by x0 plus y divided by y0 equal to 1. This is this format that we wanted to show here. This line here can be given by the equation x divided by x0 plus y divided by y0 equal to 1, where x0 is the x-intercept of the line and y0 is the y-intercept of the line. There are, however, issues with this method. The issues are what happens when x0 is equal to 0, y0 is equal to 0, and the cases when we have vertical and horizontal lines. When x0 is equal to 0, it means that we're passing through the point where the x is equal to 0, i.e. the origin. What this means is that given a line with x-intercept x0 and y-intercept y0, we can say that that line is going to be given by the equation that x divided by x0 plus y divided by y0 equal to 1. This equation, however, has some issues. For one, what happens when x0 is equal to 0 or y0 is equal to 0? When x0 is equal to 0, it means that our line has to be passing through the point where x equals 0. Therefore, it has to be passing through this line here. Considering that, the only ways this can happen is if we have a line that's passing through the origin like this, or a line that is vertical. When we have a line passing through the origin like this, the y-intercept is also 0, i.e. we are passing through the point 0, 0. Therefore, we have 1 divided by 0 here and another divided by 0 here. The other case, when we have a vertical line, is a little bit more complicated. In that case, when we have a vertical line, our x-intercept is still 0, in which case we have still divide by 0. However, for the y-intercept, there is no real y-intercept because this line is moving along the y-axis. It doesn't exactly cross the y-axis. So we have that issue. Another issue is when we have just a normal vertical line on its own. In this case, since this line is parallel to the y-axis, even though it has an x-intercept at this point here, it does not really have a y-intercept. It has y-intercepts at positive and negative infinity, so we cannot really put it. In the same exact way, for the horizontal lines, if we consider a horizontal line like this, it is parallel to the x-axis. Since it's parallel to the x-axis, even though it has a y-intercept like this, it does not intercept the x-axis anywhere. It intercepts it well at negative infinity and infinity. It intercepts it really far away because parallel lines do not intersect each other. So therefore, this line method still has issues in that it cannot be used to represent lines that are going through the origin or lines that are vertical or horizontal. So we have this issue. The next format, however, solves this issue and it gives us a much more flexible method to write out the equation of a line. The line format I'm talking about is the format of a times x plus b times y plus c equals 0, where a, b and c are elements of the real numbers. This line format is very robust, very normal, very simple and very useful in that it can give us some interesting results. In fact, the entire rest of this video is going to be dedicated to be talking about this line format here. The first thing we're going to be discussing is finding the intersections of two lines. Let's suppose a line L1, let's say L1 is given by a1x plus b1y plus c1 equal to 0, where a1, b1 and c1 are some constants. Furthermore, a second line L2 is given by a2x plus b2y plus c2 equal to 0, where a2, b2 and c2 are some other constants. In order to find the intersection points of these lines, all we need to do is to figure out the point for which the first equation is true and the second equation is true, because that's what an intersection is. An intersection is a point where the two graphs agree on what their results should be. The first graph result is true and the second graph result is true. Therefore, for these two lines, the first line's result should be true at that point and the second line's result should also be true at that point. So then, taking both of these as true, let's consider this thing as equation number 1 and this thing as equation number 2 and try to solve them like simultaneous equations. Considering this, let's take this thing and suppose L1 and L2 intersect at the coordinates x0, y0. So therefore, at these coordinates, both the first equation and second equation are satisfied. Therefore, we could extend this into saying that a1 times x0, a1 x0 plus b1 y0 plus c1 is equal to 0. And furthermore, a2 x0 plus b2 y0 plus c2 is equal to 0. This is just saying that this point satisfies both the first equation and the second equation. From this first equation here, let's try to isolate the value of y. So what I'm going to do here is rearrange this thing to get y on one side. Taking this a1 x0 term and c1 term to the other side, we get b1 y0 equal to, and on the right side we get negative a1 x0 plus c1. Dividing both sides by b1, we get y0 equal to negative a1 x0 plus c1 divided by b1, provided of course that b1 is not equal to 0, because if b1 is equal to 0, we get a different result that we can solve differently. So instead, let's just assume that b1 is not equal to 0, which means that y can be represented in terms of x like this. Given this, let's now call this equation number 3 and substitute equation number 3 into 2. So let's do 2, 3. If we do 2, 3, what we get is a2 x0 plus b2 times the value of y0, which is negative a1 x0 plus c1, all divided by b1's value, and that thing plus the final constant c2. So c2 equal to 0. Now, let's multiply both sides, everything by b1, assuming of course that b1 is not equal to 0, which is what we thought initially. And given this, let's try to multiply everything out and get our answer. Doing so, multiplying b1 by everything by b1, the first term becomes a2 times b1 times x0, and the second term becomes b2 times this thing divided by b1 times b1. So the b1 cancels out with the b1 we multiply by, leaving us with just b2 times this thing here. The first part of that is going to be b2 times negative a1 x0. So I'm going to write that as a1 b2 x0, as in a negative a1 b2. Actually, we'll cut this plus here and put a minus there directly. I don't want to put a plus and then a minus. So we have minus a1 b2 x0. The next part of that is going to be b2 times negative c1. So that's going to be negative b2 c1. And then when we multiply everything by b1, this very last term is going to be b1 times c2. So positive b1 c2, and that's going to be equal to 0. Rearranging, we can see these first two terms contain an x0. If we factor that out, then a2 b1 minus a1 b2 times x0 is equal to, and on this side we're going to take these two terms to the other side. So this b1 c2 becomes negative b1 c2, and this negative b2 c1 becomes positive b2 c1. So we have b2 c1 minus b1 c2. Dividing both sides by this thing here, we get that x0 is equal to b2 c1 minus b1 c2 divided by a2 b1 minus a1 b2. Now here we can see this thing will not be valid if a2 b1 is equal to a1 b2, i.e. if the two lines are parallel to each other, because if a1 b2 is equal to a2 b1, it means that the two lines are going to be parallel to each other. So now let's do a similar thing to try to find y0. In order to find y0, what we're going to do is take these equations, isolate x0 from the first equation, substitute that into the second equation and use it to find our answer. So here, from this equation, we can isolate a1 x0 and we get this stuff to the right hand side. Getting that, let's go down here and do that. We get, actually, let's copy these two equations down and use them as reference because it's kind of difficult to use them from memory. So here we have them. Now here we can see that a1 x0 is equal to negative b1 y0 plus c1. Therefore, x0 is equal to negative b1 y0 plus c1 divided by a1. Of course, provided that a1 is not equal to 0. So now given this condition, let's call this equation number 4. And now let's use equation number 2 and equation number 4 together to try to isolate y0. So then, using 2 and 4, what we're going to do is substitute x0 value into this part here. So we have a2 multiplied by this expression, which is negative b1 y0 plus c1 in brackets, all divided by a1, and then the next term, which is b2 y0 plus c2. So we have b2 y0 plus c2, and this whole thing is equal to 0. Now what we're going to do is multiply both sides by a1 and then simplify our expressions. So here what we have is a2 times negative b1 y0 minus c1, and then when we multiply a1 into these two terms, what we get is a1 b2, which I'm going to write as a1 b2 times y0 plus a1 c2 equal to 0. Now what we're going to do is expand this thing outward and try to isolate y0. So here we can see from this thing, we have a2 b1 negative times y0, and then we have a minus a2 c1. So minus a2 c1 a plus a1 b2 plus a1 b2 y0 and a plus a1 c2 and all equal to 0. Isolating these two terms and taking the y0 out, we can see that a1 b2 minus a2 b1 multiplied by y0 is equal to, taking this stuff to the right side, we can see we have negative a2 c1, which becomes positive a2 c1 on the other side, so a2 c1. This a1 c2 becomes negative a1 c2 on this side, so negative a1 c2, and we can finally see that y0 must be equal to a2 c1 minus a1 c2 all divided by a1 b2 minus a2 b1. Once again we can see if a1 b2 is equal to a2 b1, we do not have an intersection. In the other cases we have an intersection. So therefore this is the y coordinate of intersection, and up here we found the x coordinate of intersection. We can copy these two down and say finally what the coordinates of intersection are. So we're going to copy these two and we're going to use them to say finally that as a conclusion, given lines, and we'll say L1 given by a1x plus b1y plus c1 equal to 0, and L2 given by a2x plus b2y plus c2 equal to 0, they intersect at the coordinates. And now we're going to substitute the coordinates here. This right here is the x coordinate that we found, comma, and then the y coordinate that we found. So comma, y coordinate that we found. The y coordinate that we found is this thing here. So we're going to take that, copy it, control V it into here, and we can see that this is valid when we do not have a1 b2 minus a2 b1 equaling 0. So we're going to take this to the left. We're going to say this is valid for a1 b2 not equal to a2 b1. So then we have this condition. Given this condition, the two lines intersect at this point here. Shall we take a look at why this condition is necessary? If we consider the equation ax plus by plus c equal to 0, we can see that we can rearrange this into the y equals mx plus c format. If we take these two terms to the right hand side, this ax and c terms to the right hand side, we can see that by is equal to negative ax minus c. Therefore, y is equal to negative a over b x and then minus c over b. Here we can see this is of the form y equals mx plus c. Therefore, this right here is the gradient. So we can write this is the gradient m, and this term right here is the intercept. So we can write intercept. Now then, if two lines are parallel to each other like this, we know that they do not intersect anywhere. Given two lines are parallel, we know that they have the same gradient. Therefore, m1 equal to m2. If we consider the gradient of the first line was a1x plus b1y plus c1. Therefore, according to this pattern, the gradient of the first line, which I am going to call m1, is equal to negative a1 divided by b1. The second gradient, which I am going to call m2, is equal to negative a2 divided by b2. Now then, the condition for the intersection to exist is that these two gradients should not be equal. So then we can see, if these two gradients are not equal, we have negative a1 divided by b1 not equal to negative a2 divided by b2, and then this means that the equality is negated. So if we consider, instead of the not equal case, if we consider when it's equal and then we negate it finally, we can see that we can cut the two minus signs. We get a1 divided by b1 equal a2 divided by b2, which we can then rearrange to get a1 b2 equal to a2 b1. Therefore, if this condition is there, if a1 b2 is equal to a2 b1, then we do not have an intersection. This is exactly the reason why we should not have a1 b2 equal to a2 b1. It becomes an emergent property that over here, when a2 b1 is equal to a1 b2, we do not have an intersection because we have a divide by 0. So there we have shown that this equation gives you the intersections unless you don't actually have any intersections. If there are no intersections, it will give you a divide by 0 error. So what we've been talking about so far is only the line. We've only been talking about the line that goes ax plus by plus c equal to 0. What we're going to do next is consider points that are not on the line. So here this equation represents all points that are on the line, and therefore the equation ax plus by plus c not equal to 0 would represent all points that are not on the line. However, this not equal to 0 can also be written as 1 greater than 0 and another ax plus by plus c less than 0. This is the same exact thing. This union of these two conditions is the same exact thing as ax plus by plus c not equal to 0. However, we're going to be considering them separately. Each of these have their own idea. This right here is one region on one side of the line, and this right here is another region on the other side of the line. Basically, the line divides the space, the 2D space that we inhabit, the coordinate plane, into two regions. We have the region that is on one side of the line like this, and the other region that is on the other side of the line like this. These two regions are completely separate, and you cannot go from one region to another without crossing the line ax plus by plus c equal to 0. So now then, if we have this, what we're going to do is to consider when we have 2 points that are on the same side of the line and 2 points that are on different sides of the lines, and how we can figure out whether 2 points are on the same side or different sides of the line by using the fact that we know the value of ax0 plus by0 plus c for that given point, let's suppose x0, y0. So now let's go and take a look at that in a desmos graph and try to understand the relationship that we have here. So here we have a desmos graph. This desmos graph is showing you the line ax plus by plus c equal to 0. That line here is this dark black line that we're having over here. You can check this file for yourself. It's linked down in the description, and you can tinker around with it and play and see what kind of things you can get. Here we can see with these 3 sliders I can control the shape of this line. I can control B, A and C and move this line around into different positions. So then we can move this line around. We have full control over this line. Let's now examine what this red region here and this blue region here are. The red region is the region for which ax plus by plus c is greater than 0, i.e. it is one of the 2 regions on either side of the line. This side is the side where we have this value ax plus by plus c greater than 0. The other region of points that are not on the line are the region of points for which ax plus by plus c is less than 0. They are the ones that are denoted by the color blue. So here you can see this black line here is separating the coordinate plane into a red region and a blue region. Within the red region, if you have a point, this product this sum ax plus by plus c for that particular point is going to be positive. If you have a line in point in the blue side, its corresponding sum is going to be negative. Now then, we have 2 points here in the coordinate plane that you can drag around with your mouse like this. If we put these 2 points on the same side of the line, as in the same region, in the case where they're both in the red region, this thing's sum is positive and this thing's sum is positive. Let's suppose that P is x1, y1 and Q is x2, y2. Then P's sum ax1 plus by1 plus c is going to be greater than 0. In the same way that P's value is positive, if we take Q and say that Q is x2, y2, then a x2 plus by2 plus c is also going to be greater than 0. So therefore, if we multiply the two together in this case, we get a positive value times a positive value, which is going to be a positive value. If instead we take both of these points to the same side, but now they are on the minus side, now the value corresponding to P is going to be negative and the value corresponding to Q is going to be negative. Therefore, ax1 plus by1 plus c is going to be negative and ax2 plus by2 plus c is going to be also negative. Therefore, multiplying the two together will give you a positive number, because a negative number times a negative number is equal to a positive number. So in this case as well, we can see that the product of those two sums is going to be positive. Therefore, we can see if you have these 2 points on the same side of the line, then the product of those two sums that we described, ax1 plus by1 plus c and ax2 plus by2 plus c is going to be positive. However, if we have one of these points on one side of the line and the other point on the other side of the line, as in to get from one point to the other point you need to cross the line, we can see in this case P's sum here is positive, Q's sum is negative, therefore the product of those two sums will be negative. Similarly, if P is on the negative side and Q is on the positive side, then Q's sum is going to be positive, P's sum is going to be negative. When you multiply them together, you get a negative value. Therefore, if the 2 points are on opposite side of the lines, then that corresponding product of the two sums is going to be a negative number. So in conclusion here, what we can now do is say that if P is some point, we'll say x1, y1, and Q is some point, let's say x2, y2, then if P and Q are on the same side of the line as we just found, either both of their corresponding sums are positive or both of their corresponding sums are negative. When we multiply the two together, we get a positive value. So we can say that if P, Q are on the same side of the line, given this condition, we can say that the sum corresponding to the first one, which is ax1 plus by1 plus c, multiplied by the second one, which is ax2 plus by2 plus c, is going to be positive. As in, either both of them are positive or both of them are negative, meaning they are on the same side of the line. However, as we found above, if they are on opposite side of the line, then one of them is going to be positive, the other is going to be negative, meaning that the overall product is going to be negative. So we can say if P and Q are on opposite sides of the line, then in this case the first one's sum, which is going to be ax1 plus by1 plus c, and then the second one, which is going to be ax2 plus by2 plus c, is going to be negative, as in one of them is positive, the other one is negative, therefore the overall product is going to be negative. So then we can write this as a theory, and we can say, given a line in this form of ax plus by plus c equal to 0, and given 2 points P as x1, y1 and Q as x2, y2, we can say that if P and Q are on the same side, then ax1 plus by1 plus c times ax2 plus by2 plus c is going to be positive. If they are on opposite sides of the line, then ax1 plus by1 plus c times ax2 plus by2 plus c is going to be negative. The next thing we're going to be considering in terms of this format of line has to do with this here. This is the intersection point of two lines of that format. What we're going to do now is consider other lines that pass through that same point. So then, going back, what we had in that condition is a line L1, let's say L1, which is correspondent to the equation a1x plus b1y plus c1 equal to 0, where a1, b1 and c1 are certain constants, and the other line L2 was correspondent to a2x plus b2y plus c2 equal to 0. At the intersection point, this equation was true and this equation was true. So therefore, at that intersection point, since both of these equations are true, they must both be passing through that point. So then, if we have any other line which is also passing through that point, for it, this kind of equation should also be true. So if we have a line, let's say L3, corresponding to a3x plus b3y plus c3 equal to 0, then for that line, its values a3x0 plus b3y0 plus c3 should be equal to 0 at x0, y0, where x0, y0 is the intersection of the first two lines. Now then, there is actually an easy way to find L3. In fact, we can find an infinite family of L3s. It is simply to take that L3 is equal to m times, is correspondent to m times a1 x plus b1y plus c1 plus n times a2x plus b2y plus c2 all equal to 0. Why would this be valid? Well, in the case where we are at the intersection point, let's say x0, y0, let's say intersect at x0, y0. In this case, at x0, y0, this term we know to be 0 and this term we know to be 0. So therefore, for some real constants n and m, this part 0 and this part 0, therefore the whole thing is 0. Therefore, this statement is true. So therefore, L3 would also pass through the point where L1 and L2 intersect. So here the only condition is that n, m should be elements of the real numbers, and we also should not have m and n both being equal to 0, and also m and n both should not be 0. One of them can be 0, but both of them should not be 0, because if both of them are 0, we just have on the left here 0 times something and on the right here 0 times something. So it really doesn't matter what's inside these two brackets here, because for any such values x and y, this statement will be true. So here m and n both should not be 0. However, one of them can be 0 while the other is some value. And of course, if one of them is 0 while the other is some value, then what we have is basically either L1 or L3. Because if we have L1, then we have some real constant times L1's value, which is then going to be divisible. So we can divide out the n, meaning we just have a2x plus b2y plus c2 equal to 0, which is exactly L2. Or in the other case, when n is equal to 0, if m is some real constant, then we can divide both sides by m. Dividing 0 by m does nothing because m is not equal to 0. In which case, we just have a1x plus b1y plus c1 equal to 0, which is L1. So here we can see m and n are real numbers. M and n both cannot be 0 at the same time, but one can be 0 while the other is non-zero. So that is how we find the lines that are passing through a given point. Any line passing through a given intersection point of two other lines, L1 and L2, can be written as a linear combination of L1 and L2. It is m times L1 plus n times L2 equal to 0, where n and m are real constants and m and n both should not be equal to 0 at the same time. However, of course, one can be 0 while the other is non-zero. That's not a problem. However, both of them cannot be 0 at the same time. Let's now visualize this with another desmos graph to help you better understand this concept. So here we have a desmos file that I have created. This file is there to represent two lines, which are the red line and the blue line, and the intersection of them, and also another line which is going to be the purple line, which is some combination of the red line and the blue line. Here you can check this file as well. Its link is down in the description if you want, and play around with it. On the left here, we can see all the values that we have in here. These A1, B1 and C1 are the constants of the line 1. A2, B2, C2 are the constants of line 2. And M and N are the proportionalities at which we add the two lines to make a third line. So here you can see, if I change A1, if I take this slider for A1 and I move it back and forth, only A1 changes, and as A1 changes, since the purple line is proportional, as in it's not proportional, it's dependent on the first line, line 1, it is also changing. If instead I change line 2's constants, you can see line 2 changes and line 1 doesn't change. And furthermore, if I go down here and I change M and N, you can see that the corresponding line of the purple line is also changing. You can see as we change these constants, the purple line is changing. So you can play around with this and try to figure out different interesting things. We can see here basically the basic idea of showing this is that when we have this linear combination, no matter what A, B and C are of lines 1 and 2, we can change this to any values we want. However, as we do that, we can see that no matter what, this line, the purple line, is passing through the intersection of the other two lines. You can see what happens when we add different constants for M and N, and we can see what happens when we try to make M and N both equal to 0. So if we try to do that, let's actually try to do that just for observation. You can see if we make M equal to 0 and we try to make N equal to 0, the line disappears. The reason this line disappears is because now we no longer have any dependency on X and Y. Here, since M is equal to 0, this whole term is equal to 0 no matter what X and Y are. Similarly, since N is equal to 0, this whole term is equal to 0, since again, it doesn't matter what X and Y are. So therefore, desmos just doesn't render it anymore because there's no dependency on X and Y. If we bring the constants back, we can see we have now the line, the purple line, back again. So in conclusion, if we have two lines L1 and L2, where L1 is of the form A1x plus B1y plus C1 equals 0, and L2 is of the form A2x plus B2y plus C2 equals 0, and suppose they intersect at x0, y0, given that any other line that also intersects the point x0, y0, as in passes through the point x0, y0, can be given by m times the first function's equation, as in m times a1x plus b1y plus c1, plus n times the second function, or n times a2x plus b2y plus c2 equal to 0, where m and n are two real numbers and m and n cannot both be equal to 0 at the same time. Because if m and n were both equal to 0 at the same time, then on the left, 0 times this thing would be independent of x and y, because 0 times anything, whether it be 0 or non-zero, is going to be 0. Similarly here, if this is 0, this is also going to be 0, meaning that the whole expression would be independent of y, meaning that there would be no point in the expression. It would be true everywhere. It would be independent of y and true everywhere, irrelevant of the value of y, and same with x. Due to this, we want to limit m and n and say that m and n should not be equal to 0 at the same time, and any other combination is alright. Now let's go to another topic before we continue with a few examples and some more important proofs. So then, first off, what we're going to do is find a parametric way to write an equation ax plus by plus c equals 0 in parametric format. So let's say we have the line L, which is given by ax plus by plus c equals 0. And let's suppose that the point x0, y0 is on L. Given this, we also know that ax0 plus by0 plus c is equal to 0. So we know that for any general x and y, this is the case, and for the specific x and y, it's also the case. From these two, 1 and 2, we can say that ax plus by plus c for some general x and y must be equal to ax0 plus by0 plus c for the specific x0 and y0 that we know are on this line. Given this, we can now rearrange this. What we're going to do is cut the two c's, the plus c and the plus c. We're going to take the x and the x0 to one side as a x minus a x0. We're going to take the by and the by0 to other side and write is equal to by0 minus by. Now what we're going to do is factor out the a and the b. Write this as a times x minus x0 and write the other thing as b times y0 minus y. Now here what I'm going to do is factor out negative from the right hand side and write a x minus x0 is equal to negative b y minus y0, so that we have that format of y minus y0 x minus x0. We're going to now divide both sides by ab. So here we need the a and b's as we require to be non-zeros. When we do this, we get x minus x0 divided by b is equal to negative y minus y0 divided by a. Now then, let us suppose that this is equal to a parameter t, where t is an element of the real numbers. In this case, we can see that x minus x0 divided by b is equal to t and negative y minus y0 divided by a is equal to t. This gives us that x minus x0 divided by b is equal to t, meaning that x is equal to bt plus x0. This also gives us that negative y minus y0 divided by a is equal to t, meaning that y minus y0 is equal to negative at, and finally y is equal to y0 minus at. Here what we have are the parametric equations of a line of the form ax plus by plus c equals 0. So we can use this wherever we want. We can define some parameter t and then express x in terms of t, y in terms of t, and then plug in different values of t in order to find different values of x and y that satisfy this line. I.e., we can make a kind of slider where we can change only t, and as we change t, x changes and y changes according to this expression that we have here. The next thing we're going to be considering is the perpendicular distance of a point from a line. We're going to have this line in the form of ax plus by plus c equal to 0. And let's suppose this external point that we want to find the perpendicular distance of is having coordinates of h, k. So then, given this, the distance we are looking for is this perpendicular distance here. I'm going to mark the 90-degree angle here, and let's suppose that this perpendicular distance's length is p. Now, what we're going to do here for this thing is to construct a vertical down from this point, external point, onto this line. Now if this point is below the line, of course the vertical will be in the upward direction. If not, it's in the downward direction as such, and we're going to construct this line. Also note, it is possible that this line does not intersect this other line here, and that happens if both of these lines are vertical, as in this line here is vertical, which only happens if out of these coefficients this coefficient is equal to 0, but in that case the answer still comes out, so don't worry about that condition. Assume this thing is non-vertical for now, in which case there will be some kind of intersection like this. Let's call this point, we'll call it capital A. Let's call the point we're interested in capital B, and this point here capital C. So then, since this line we dropped AB is a vertical, it means that the coordinates of A, the x-coordinate of A and the x-coordinate of B are the same. So therefore A is h, and then some y-coordinate. Considering this thing, it must satisfy this equation here. So therefore we have A times h plus B times, I'll call this coordinate y dash temporarily, plus C must equal 0. Therefore by dash must be equal to negative ah minus C, meaning that y dash must be equal to negative ah plus C divided by B. We can substitute this value in and say that the coordinates of the point A are h, negative ah plus C divided by B. So then these are the coordinates of the point A. Now then, consider the distance AB. The distance AB from the Cartesian coordinates we know is going to be equal to the square root of the square x coordinate differences and the square y coordinate differences added together. In terms of x coordinate differences, we have h minus h squared, which is going to be 0, and then the other part, which is the y coordinate differences, I'm going to write as k minus the other coordinate, which is negative AH plus C divided by B whole thing squared. Evaluating this out, the first part is going to be equal to 0. The second part is going to be K minus the negative part here, which we are going to cut and write as a positive part. So here what we have is K plus AH plus C divided by B whole thing squared. Now then, simplifying this down, we can take the B and multiply it by the K to get the square root of AH plus BK plus C divided by B squared. Now then, we have something on the inside squared and then being square rooted. This is the same as taking the absolute value, because when you square and square root a number, you are essentially removing its sign. So this right here is the absolute value of AH plus BK plus C divided by B. I'm going to distribute the absolute value sign to the top and bottom and write this as the absolute value of AH plus BK plus C divided by the absolute value of B. We're going to call this equation 1. So therefore we have that the length AB is equal to absolute value of AH plus BK plus C divided by the absolute value of B. Now let's consider a horizontal drawn from the point A like so. And let's consider that this horizontal is an angle theta. So let's suppose this angle here is theta. Then this angle here would also be theta. Now then, let's consider what the tangent of theta is. From this thing, we know that the gradient of this line, gradient from earlier we found, is equal to negative a divided by b. If you want proof of that, just rearrange this thing into a y equals mx plus c form. You see that m will be equal to negative a divided by b. Therefore, the tangent of theta must be equal to negative a divided by b. So down here we can write after this point that the tangent of theta must be negative a divided by b. If we instead consider the absolute value of the tangent of theta, the absolute value of tangent of theta is going to be the absolute value of a divided by b, which is going to be the absolute value of a divided by the absolute value of b. Now then, recall that the absolute value of tangent of theta is the tangent of the absolute value of theta. So the tangent of the absolute value of theta is going to be the absolute value of a divided by the absolute value of b. We can turn this into a triangle. If we turn this into a triangle, the triangle we get is going to have some kind of right angle somewhere. One of the angles is going to be theta, in which case, if that angle is theta, and if one of the side lengths, this side length is the absolute value of b, this side length would be the absolute value of a. So here is the absolute value of a here, the absolute value of b here, and theta here. Considering this triangle, the hypotenuse here is the square root of the absolute value of a squared plus the absolute value of b squared, which is going to be the square root of a squared plus b squared. Since the absolute value of a squared is the positive value, when you square it, you just get the same thing as when you square a. Since a is a real number, a squared is going to be absolute value of a squared. Same thing with b. Absolute value of b squared is going to be equal to b squared. So therefore the hypotenuse here is going to be a squared plus b squared, where this angle here is the absolute value of theta. Now then, consider what the cosine of absolute value of theta is. The cosine of the absolute value of theta is going to be the absolute value of b divided by the square root of a squared plus b squared from this triangle. The absolute value of b is the adjacent and this thing is the hypotenuse. Now then, considering our geometry here, the length p which we require is this length AB cosine of theta. Therefore, let's consider the length BC, and let's say that BC is going to be AB times the cosine of the absolute value of theta. So therefore, BC as in P is going to be equal to AB times the cosine of the absolute value of theta. Again, this is not a problem, since we know that the cosine of theta and the cosine of absolute value of theta are the same thing. Now then, considering this, we can now substitute these values in. If we call the equation with the cosine of the absolute value of theta as 2 and this other equation as 1, substituting those two in, we can see that 1 gives us that AB is absolute value of AH plus BK plus C divided by absolute value of B. So here we have the absolute value of AH plus BK plus C divided by the absolute value of B, and the cosine of the absolute value of theta, which is the same as the cosine of theta, is equal to the absolute value of b divided by the square root of a squared plus b squared. Cancelling out this absolute value of b, assuming the absolute value of b is not equal to 0. Again, that's the issue with the vertical case, but in the vertical case it still works, so it's not a problem. We get finally that this length p, the perpendicular distance of the point to this line, is the absolute value of ah plus bk plus c divided by the square root of a squared plus b squared. Now then, in summary, what this means is that if we have a line, let's say we have a line like this, and we have a point which is a perpendicular distance which I'm going to draw, a perpendicular distance p away. If this point is given by h comma k and this line is given by ax plus by plus c equals 0, then we can say that the perpendicular distance of this point is going to be the absolute value of ah plus bk plus c divided by the square root of a squared plus b squared. You can see, instead of the x value of the line, we substitute the x value of this external point. Instead of the y value of the line, we substitute the y value of the external point, and just write this value and find its numerical value. So therefore, this right here is the expression for the perpendicular distance of a point h comma k away from a line of the form ax plus by plus c. And now let's review that other exception case which I didn't talk about. We're going to review it in brief because it's not that much to talk about. The exception case is when we couldn't draw the vertical, in which case we couldn't cancel that absolute value of b, since the absolute value of b is equal to 0. This line is a line of the form ax plus c equal to 0. In this case, the b part is 0, so we're going to remove it from our equation. And in this case, this point here is going to be h comma k. Now then, here we have a line of this format. If we write this out, x is going to be equal to, taking this to the other side, negative c divided by a. So here, anywhere along this line, x coordinate is equal to negative c divided by a. So along this line, x is equal to negative c divided by a. For this point, its coordinates are h comma k. So then, here, since this line is a horizontal, the only things that are relevant for our length are the x coordinates h and negative c divided by a. So therefore, if we consider this thing as p is going to be the absolute value of the difference of h and negative c divided by a. So therefore, this is what we're looking for. We're looking for h minus c divided by a, which is going to be the absolute value of taking this a up. We can see this is ah plus c divided by a. And we can see, if we substitute b equals 0 into here, this thing goes to 0, this thing goes to 0. On the bottom we have the square root of a squared, which is going to be the absolute value of a. On top we have ah plus c absolute value. We can see that is exactly what we get here. So in that special exception case, also this formula works out. Therefore we can say that this formula is valid for all a, b and c, and for any point h comma k that is not on the line of ax plus by plus c. The next thing we're going to be discussing is the perpendicular distance between two parallel lines of the form ax plus by plus c equal to 0. This first line, let's write it as ax plus by plus c equal to 0. And for the second line, since a and b's ratio must be the same for this line to exist like this and for this line to exist like this in parallel, as in their gradients must be the same, therefore their a to b ratio must be the same. Let's write the second line as being ax plus by plus d equal to 0. So the only thing that can change is the other constant that we add. So let's suppose this is the case. Let's suppose one of the lines is ax plus by plus c equals 0 and the other line is ax plus by plus d equals 0. And let's now once again do a little construction to try to find this perpendicular distance. So then, let's suppose this angle here is theta. And then therefore this angle here would also be theta. And this is a 90-degree angle. If this is a vertical, let's suppose that this point here is at x coordinate x0. Therefore this other point which is on the same vertical would also have x coordinate x0. However, when we rearrange this equation to get y, we know that y is going to be equal to negative ax minus c divided by b. So therefore for this first one, its corresponding y coordinate would be negative ax0 minus c divided by b. The second one's x-coordinate, y-coordinate correspondent would be negative ax0 minus d instead of c divided by b. Now then, let's label this point here, let's call it capital A, this point here capital B, and this point here capital C. Consider the length AB. Considering the length AB, we know that since AB is a vertical, the x-coordinates don't matter, and all we want to do is take the absolute value of the difference of the y-coordinates. So let's do that. Let's take the absolute value of the difference of the two y-coordinates. The first y-coordinate is negative ax0 minus d divided by b, so we'll write it as negative ax0 minus d divided by b, minus the second y-coordinate, we'll put this in brackets to make it easier. The second y-coordinate is going to be negative ax0 minus c divided by b. Now then, simplifying this out, we'll take these things out as separate factors. Here we have negative ax0 divided by b and a negative d divided by b. Separating them, we get the absolute value of negative ax0 divided by b and minus d divided by b. And then over here, this negative cancel to give us a positive ax0 divided by b, and this negative cancel to give us a positive c over b, absolute value. Now then, looking at this, we can see this term and this term cancel, leaving us with just a c divided by b and a negative d divided by b. Taking them under a common base, we can see that this is equal to c minus d divided by b, which I'm going to write as the absolute value of c minus d divided by the absolute value of b. Once again, by considering what the tangent of theta is, we know that the tangent of theta is negative a divided by b. So writing that separately, we can call this equation 1. We know that AB length is equation 1, and considering the tangent of theta separately, we know that tan theta is going to be negative a divided by b. So the absolute value of tan theta is going to be the absolute value of a divided by the absolute value of b. Therefore, the tan of the absolute value of theta is going to be the absolute value of a divided by the absolute value of b. Constructing this triangle, it looks like this. We have the absolute value of b over here, the absolute value of a over here, this angle being the absolute value of theta, and this length here being the square root of a squared plus b squared. Again, we can write a squared plus b squared here instead of absolute value of a squared and absolute value of b squared, because the absolute value of a squared is the same as the a squared value. Now then, considering the cosine of the absolute value of theta, we know that the cosine of the absolute value of theta is going to be the adjacent, which is b absolute value divided by the square root of a squared plus b squared. Therefore, this is that value. And here, since we know that the cosine of the absolute value of theta is the same thing as the cosine of theta, since cosine of theta is symmetrical about the x-axis, we can say that the cosine of theta over here, we will write the cosine of theta, is itself the absolute value of b divided by the square root of a squared plus b squared in this case. Now then, for this thing here, we know that this length here, which I'm going to label p, is going to be this length AB cosine of theta. So therefore, we can write that P or BC, P equals, actually AC here, P or AC is equal to the value of the length AB times the cosine of theta. The value of the length AB from the first equation here is c minus d divided by the absolute value of b. So we can write that this is equal to absolute value of c minus d divided by the absolute value of b multiplied by, and the second value, the cosine of theta, is the absolute value of b divided by the square root of a squared plus b squared. Cancelling these two out, what we are left with is simply the absolute value of c minus d divided by the square root of a squared plus b squared. Therefore, if we have two parallel lines which are of the form, let's say these two lines, they are parallel. This first line is of the form ax plus by plus c equals 0, and the second line is of the form ax plus by plus d equals 0. Then the perpendicular distance p between them is going to be equal to the absolute value of c minus d divided by the square root of a squared plus b squared. This thing can occasionally pop up in some locations, which is why I am teaching it. You can use it as you wish, wherever required. The next and final topic we're going to be talking about is angle bisectors of two lines. Suppose we have two lines which are a1x plus b1y plus c1 equals 0 and a2x plus b2y plus c2 equals 0. Let's suppose that this one is called L1 and this one is called L2. Given this, when these two lines intersect, provided of course that they are non-parallel, we will have two angles like this. This is one angle and this is one angle. This angle here, let's call it alpha. It's mirrored on this side as alpha. There's another angle here, it's beta. It's mirrored on this side as beta. So then we have two angles. These angles can be bisected by two lines. The angle alpha can be bisected by a line which I'll draw out now. It's a line that's going to look something like this. It's going to look something like that. There's another angle bisector for the other angle, and that angle bisector will look something like this. What we're going to do now is find the equation corresponding to these two angle bisectors and use them to figure out which of the angle bisectors is bisecting the big angle and which of the angle bisectors is bisecting the small angle. So then, considering this, what is an angle bisector? Well, it's a line that bisects an angle, as in it breaks the angle into two equal pieces. What kind of properties does something like that have? Well, if you take a look here, we can see something interesting which we can use in order to find what the equation of this line must be. So now, considering this thing here, you can see, if we consider any point on this line here like this, let's mark it out like that, and we consider this point here. If we draw perpendicular to this first side, we have something like this. If we draw perpendicular to the other line, L2, we have something like this. Now then, these two triangles that we just drew are sharing a common side, which is this hypotenuse here. They are also sharing an angle because remember, since this line bisects this angle alpha, each of these is going to be of angle alpha divided by 2. So this is alpha divided by 2 and this is alpha divided by 2. And because of this, this side length is going to be equal to this side length because, well, all we have is this angle, which we then need to take the cosine of to get this side length and this side length. So both of them are going to be equal. And this length are going to be equal. That is the more important part. Given this condition, this length here and this length here are going to be equal. Similarly, if we consider any point on this second angle bisector and draw the two perpendiculars like this, we can see once again, since this is an angle bisector, this angle here is divided into two pieces of equal size. Therefore, if we consider this angle a component, this angle is beta divided by 2 and this angle here is beta divided by 2. These two triangles that we just drew here share a common side, which is this hypotenuse here. Therefore, this length and this length are also equal. So we can mark them as this length and this length are also equal. So it seems the property that we have here is that if we have any point, let's say x1, y1 on the first angle bisector or a second point x2, y2 on the second angle bisector, both of these share the property that their distances to each of these two lines L1 and L2 are equal. For the first thing, let's suppose that this distance is d1. We'll call this d2. We call this distance d1. We'll call this distance here d4 and this distance here d3. Considering this, let's write out d1, d2, d3 and d4 and figure out what them being equal means. So then, d1 is the distance of x1, y1 to the line L1. We know how to do this equation because we just found how to find the perpendicular distance of a point from a line of this form. So then, d1 is equal to the absolute value of into this equation of L1, we need to substitute these points here. So therefore what we have is a1 x1 plus b1 y1 plus c1 divided by the square root of a1 squared plus b1 squared. Considering then d2 is that distance to the point L2 to the point x1 y1 of the line L2. Then all we need to do is substitute these 2 points into this thing and divide by the square root of a2 squared plus b2 squared. Therefore, d2 length is going to be equal to the absolute value of a2 x1 plus b2x1 y1 plus c2 all divided by the square root of a2 squared plus b2 squared. So then, what we need is for these two to be equal. Therefore, in this case, the condition here is that a1x1 plus b1y1 plus c1's absolute value divided by the square root of a1 squared plus b1 squared must be equal to the absolute value of a2x1 plus b2y1 plus c2 divided by the square root of a2 squared plus b2 squared. This is the first condition that we seem to be getting for this angle bisector here. Let's now see what condition we require for this angle bisector, the second one, as in the second angle bisector, the angle bisector of beta. For that one, d3 must be equal to d4. Considering d3 is x2 y2's distance from L1 and d4 is x2 y2's distance from L2. Therefore, using the same formula that we derived earlier, we can say that d3 must be equal to the absolute value of, we are considering x2 y2 from L1, so therefore this is a1 x2 plus b1 y2 plus c1 divided by the square root of a1 squared plus b1 squared, and similarly d4 is going to be equal to the distance of this point x2 y2 to L2, which is going to be then equal to a2 x2 plus b2 y2 plus c2 divided by the square root of a2 squared plus b2 squared. Now then, we can see that once again, for this thing to be true, our condition required is that a1 x2 plus b1 y2 plus c1 divided by the square root of a1 squared plus b1 squared be equal to the absolute value of a2 x2 plus b2 y2 plus c2 divided by the square root of a2 squared plus b2 squared squared. So then, we can see from these two, if we consider the two conditions we need, this is the condition for the bisector of alpha, this is the condition for the bisector of beta, we can see both of these have the same exact condition. Replacing the x's with generic x's, let's say instead of x1 I just have x, so here we can cut this one, here we can cut this one, because there's nothing special about x1, it's just some point on this line. Same thing with y1, we cut this one here. Similarly down here, let's cut this x2 and get the generic form of the line, which is the bisector of this thing. We get this thing here and this two here. We can see that the condition for the angle bisector of alpha and the condition for the angle bisector of beta are in fact exactly the same. So therefore, if we graph this thing, what we're going to get is the same equation for both of these two. So in fact, if we graph this value here, we're going to get both angle bisectors together, as in both angle bisectors satisfy this equation here. So then, if both the angle bisectors satisfy this equation, how do we isolate one of the angle bisectors equation? Now obviously, this angle bisector's equation is something different from this angle bisector's equation. However, this compound equation we have here encodes both of these lines. How do we get just one line on its own? So for this purpose, I've created yet another desmos file. Here it is available in the description down below. In this file, we have two lines, the red line and the blue line. The red line is line 1, its controls are available in this folder here. The blue line is line 2, its controls are available in this folder over here. You can mess around with them, change their values and see what happens. So then, when we have these two lines like this, they create two angles, an acute angle and an obtuse angle, unless of course they are perpendicular, in which case both the angles are 90 degrees. Showing the angles here, we can see the orange angle is the acute angle and the green angle is the obtuse angle. Now then, these two angles have their own angle bisectors. For the green angle, we have this angle bisector here. For the orange angle, we have this angle bisector here. We can now see these two separately. What I want is an equation for the purple angle bisect on its own and for the black angle bisect on its own. Currently we have an equation that contains both angle bisectors, as in if you write that equation and compute it, it will show you both angle bisectors together. We do not have a way to separate them yet. In order to separate these two bisectors into two separate equations, what I'm going to do is show you some regions related to the red line and the blue line. Recall from earlier that if the red line is of the form a1x plus b1y plus c1 equal to 0, we could have values for when it's greater than 0 and when it's less than 0, which manifest themselves in terms of two regions, one on the one side of the line and another on the other side of the line. The same thing can of course be done with line 2. What I'm now going to do is show you those regions. For the red line, hiding the angles, I'm going to now highlight the regions corresponding to the red line. Here we can see there's a green region and an orange region. If we open this up, we can see the green region is corresponding to a1x plus b1y plus c1 being greater than 0, and the orange region is corresponding to a1x plus b1y plus c1 being less than 0. Similarly, hiding that, I can also show the regions for the blue line. For the blue line, these are the regions. Again, it's the same definitions. For the blue line, if we look, the green region is the region for which it's positive, and the orange region is the region for which it's negative. Highlighting both of these at the same time, we can see we get some interesting colors. Here we can see on this bottom left here, we have a deep or a reddish orange color, and on the right side here, we have a deeper green color. And in these two other regions, we can see we have the same color occurring. This color is a mix between orange and green. The reason for this is that within this region, both line 1 and line 2's equation, when you substitute, you get positive values. Within this region, when you substitute into line 1's equation and line 2's equation, you get both negative values. So therefore, within this region, both of the lines are positive. Within this region, both of the lines are negative. Therefore, the color is amplified when we draw these two regions on top of each other. So if I now show you one of the bisectors, you can see that this purple bisector goes through the green region and the orange region only, and of course the intersection point, but let's ignore that point and consider only the green region and the orange region. Therefore, for this line, it is corresponding to the values where both the signs of one line and the other line are both the same sign. Either they are both positive or they are both negative. Considering instead the other bisector, this bisector goes through the other two regions where we have a mix of orange and green. The meaning of this is that this line passes through the regions where one of the lines has a positive value and the other has a negative value. Here, one of them has a positive value and the other is negative. Same here, one of them is positive, the other is negative. Now then, considering this, we can use this knowledge to separate these two equations of the two bisectors into separate equations. Going back to our paper, we can see that over here, for the first thing, let's call this bisector 1. Let's call this bisector 1. Let's suppose this bisector is the bisector that goes through the regions that have the same sign, as in both oranges or both greens, as in both lines have either positive values or negative values through that region. And let's suppose the bisector number 2 goes through regions where one of the lines is positive and the other is negative. So then, considering equation 1, within equation 1, since we know both of them have the same sign, they are either both positive or both negative. In the case where they are both positive, we can remove these absolute value signs, cut them out, and just write the answer as it is. So therefore, for this thing, we could write that this is a1x plus b1y plus c1 divided by the square root of a1 squared plus b1 squared is equal to a2x plus b2y plus c2 divided by the square root of a2 squared plus b2 squared, provided that both of them are positive. If instead both of them are negative, then the absolute values, what they're going to do is stick a negative sign on both of these. As in, since the value on the inside is negative, in order to convert it into a positive value, we need to multiply it by -1. Therefore, all the absolute value will do in that case is stick a negative on front of both of these. But you can see, since a negative is stuck on the front of both of them, we can simply cancel out this negative. Therefore, we can see, due to this reason, since either both of them are positive or both of them are negative, we can see that we can actually remove these absolute value signs. In the positive case and the negative case, we get the same exact answer. Therefore, removing the absolute value signs, we can see that line number 1 is given by this equation over here. Now then, instead, let's consider equation number 2. In equation number 2, what we had is that this line passes through regions where one of them is positive and the other one is negative. Therefore, supposing this thing is positive, then we would not need the absolute value sign, so we could write it as a1x plus b1y plus c1 divided by the square root of a1 squared plus b1 squared. But in that case, if it was positive, it means that the other thing is negative, meaning the absolute value sign will stick a minus on the front, so this is equal to the negative a2x2. Actually, I made a mistake here. I have not removed these 2's here. There's not supposed to be a 2 here. We're supposed to have general x's and y's. So a2x plus b2y plus c2 divided by the square root of a2 squared plus b2 squared. The reason for this is because when this thing is positive and we can remove the absolute value sign without an issue, this thing becomes negative, which means we are forced to put a negative sign there, and therefore we have this equation here. And in the opposite case, of course, if this thing over here is positive, then this thing will be negative, which means we have the same exact thing. We can take the negative to the left or the right, it doesn't really matter, it's the same exact equation. So therefore, this is correspondent with bisector number 2. So we can see, for the first bisector we have one thing on the left, it's equal to the positive thing on the right. For the second bisector we have one thing on the left, it's equal to negative thing on the right. Therefore, for the two bisectors we can see, putting a plus or minus, that if we have two lines, let's say L1 and L2, and let's suppose that L1 is equal to a1x plus b1y plus c1 equal to 0, and the second line L2 is equal to a2x plus b2y plus c2 equal to 0. In this case, the bisectors, which this S is important because both of them are included here, are given by a1x plus b1y plus c1 divided by the square root of a1 squared plus b1 squared equal to, here to include both bisectors we put a plus or minus, and then the a2x plus b2y plus c2 divided by the square root of a2 squared plus b2 squared bit. Again, this equation can also be used wherever you want. All you have to do is state it and then apply it into your equation. And here, one of these bisectors is going to be an acute angle bisector, the other is going to be an obtuse angle bisector. You cannot easily know from the plus or minus or anything like that. You just need to find it and solve it. However, to find it and solve it, all you need to do is this simple trick. Consider any one of the lines L1 or L2. Find its gradient. Let's suppose that L1 has a gradient m1. Therefore, m1 must be negative a1 divided by b1, and m2 must be negative a2 divided by b2. Considering either of these gradients, it doesn't matter which, you can choose either one. Choosing either one, if we have an acute angle bisector, then we have something like this. Let's suppose we have the two lines like this and an acute angle bisector like this. So therefore, this angle here, let's call it alpha. This angle alpha is less than 90 degrees divided by 2, which means it's less than 45 degrees. So then, given this condition, if alpha is less than 45 degrees, we can say that the tangent of alpha is going to be less than 1. Since when we have tan alpha equal to 45, as in tan of 45, it is equal to 1. And since tan of alpha is an increasing function, we know that tan of alpha is less than 1 if alpha is less than 45 degrees. And now we can consider what alpha is. This right here is a bisector, so we can call it like a bisector. Let's suppose this is L1 and this is L2. Here we know if we have an angle between two lines, all we have to do is consider that angle, and we know the tangent of that angle is equal to the absolute value of the difference of the two gradients divided by 1 plus the two gradients multiplied together. So here, supposing this bisector has gradient MB, we know that the tangent of alpha is equal to mb minus m, let's say either 1 or 2, it doesn't matter which is which, both of them will give you the same answer, and divide by 1 plus mb times m1. Therefore, we can calculate this like this. If this answer is less than 1, it means that we have alpha being half of the acute angle. Therefore, the bisector we have is the acute angle bisector. However, if instead of that condition, if this value is greater than 1, as in we have greater than 1 here, it means that what we have instead of the acute angle bisector is the obtuse angle bisector. And in the special case where in this case it's equal to 1, we know that the two lines that we had initially are perpendicular to each other, and we have just cut an 45-degree angle out from that, as in we've cut a 90-degree angle into two 45-degree angles. So then each of these cases we know what to do. In the case where this absolute value here, the gradient of our bisector minus one of the lines gradients divided by 1 plus one of the lines gradients times the angular bisector's gradient. If it's greater than 1, we know we've cut an obtuse angle, so it's the obtuse angle bisector. If it's less than 1, we know we've cut an acute angle, so it's an acute angle bisector. And if it's equal to 1, we know two things. It's no longer an acute angle or obtuse angle bisector, it's a 45-degree angle, so therefore we have a 90-degree angle bisector, meaning that our two original lines were perpendicular to each other. So that's that. We can use each of these results wherever we want in different context. I'll just write this as a summary. If we have mb minus m1 divided by 1 plus mb m1, and if we have this thing being less than 0, we have acute angle bisector, so I'll just write acute angle. If we have mb minus m1 absolute value divided by 1 plus mb m1, then we have this thing greater than 1, it's going to be an obtuse angle, so I'll write obtuse angle. And in the case where mb minus m1 divided by 1 plus mb m1 is equal to 1, then we have the two lines are perpendicular to each other. Therefore, the bisectors that we just cut this 90-degree angle into two 45-degree angles, which is why we got the tan of 45 degrees to be equal to 1. So then, that is going to be the end of this lesson. We have a lot of theories here. I would like you to find some practical examples or some questions and try to do them using these theories. Refer back to this video if you need any assistance or further, and write down in comments down below if you have any further questions or you didn't understand something or what. I will attempt to explain. So then, that is going to be the end of this lesson here today, and thank you for watching and goodbye.